chemical equations. The first equation was okay. It seems a lot of people got that one all right. The copper with nitric acid. Actually, essentially it's nitric acid because it's copper with nitrate and acid. So it's copper with nitric acid, similar to what we did in class. And actually that was the same combination I gave you as a take-home. I'm not sure how many people did the take-home reaction, except I think I changed one thing, hydrochloric to hydroiodic acid. But anyway, that seemed to go okay, but this next one didn't seem to go so well. This was the solid sodium sulfide with, what was it, with sodium nitrate? No. Sodium nitrate. So a lot of people figured that there's going to be no double replacement reaction here. That's correct, there is no double replacement reaction, but the double replacement reaction is only one type of reaction that we look for. What are the other types of reactions that we look for? Redox and metathesis. And so here, was it sodium nitrate? What was the other reactant in that? Sodium bromide? Okay. And so this isn't all that interesting for redox, unless you know a little bit. You know, as far as redox goes, bromide is not a very good reducing agent. Sodium ions are not very good oxidizing agents. So we have sodium, we have sulfide, we have bromide. And this is an okay reducer. Okay to poor, I should say poor, okay reducer. It's like, you know, chloride. Is chloride a very good reducer? Is chloride very reactive? No, it's not very reactive. So yeah, bromide's more reactive. Iodide, however, iodide is a pretty decent reducer. You know, and the reason is chloride's small, bromide's bigger, iodide's big. So iodide, it's easy to take an electron off. And so iodide's often used as a reducing agent. And the same thing with sulfide. Oxide is a very poor reducer. You know, oxide is quite stable, O2 minus, but sulfide is a lot bigger. And so sulfide is often used as a reducer too. So sulfide is a very common reducing agent. But there's no oxidizer here because what else do we have present? We have water. And so I don't see much happening for redox here. You know, we have this is a pretty good reducer. So this is I would say, fairly good reducer. It's not on our chart, but we have to watch out because when we have sulfides with an oxidizer, it can be oxidized without too much trouble. What I see here, when I look at this mixture, you know, I see something much more reactive. What is it? What is the most reactive species you see in this list? And so the most reactive species I see is a powerful base, a very strong base. Do you see it? Automatically, when I see this, I see strong base. How come I see a strong base? Because I look at the chart. I've looked at the chart over and over again. You don't have to look at it over and over again. You know, the most important things are the strong, like the strong acids. This is why I asked you about the 7 common strong acids, but what are the strong bases? You know, amide, oxide, sulfide, hydroxide. And so when I look at this, I see strong base. What do strong bases do? Well, so this problem was multi-fold. One, is this going to stay solid when you mix it with aqueous? Are sodium salts going to stay solid when you mix it with an aqueous solution? So number one, it's going to dissolve, right? And so it'll be, all sodium salts are aqueous. So I just threw that in as an additional step. Not only did I throw that in as an additional step, if I try to write sodium sulfide aqueous, it doesn't exist. Sodium sulfide aqueous doesn't exist because sulfide is too powerful of a base to exist in water. Sulfide immediately hydrolyzes all the 100%. It's a strong base. Strong bases hydrolyze water completely. Weak bases partially hydrolyze water. Strong bases completely hydrolyze water. And so the strongest base, I mean, some people got it. They recognize this as a strong base, but they said there's no acid. Yeah, sodium isn't an acid, bromide is an acid, but water. So this was the second thing you have to recognize. There's lots of water around, and water can be a reactant too. And so here's your acid. And so strong bases hydrolyze water completely. There's a good driving force for this to make HS minus and OH minus. So this is the acid, this is the base. This is the acid going backwards, this is the base going backwards, and so we're going from stronger to weaker. So that was the reaction I was looking for. Just strong base hydrolyzes water. So this is why I couldn't write sodium sulfide aqueous, because it would just hydrolyze the water immediately. So I wrote it as sodium sulfide salt. So that was one, and then the other one was the combustion of ethanol. A lot of people got that one okay, just issues with balancing. And then the, what was it, sucrose? Or no, ethanol and the oxide. There are different ways you can burn ethanol. One, you could burn ethanol and oxygen. You know, ethanol is a great reducing agent. But we have oxidizers that are more powerful than oxygen. Can you list some oxidizers that are more powerful than oxygen? Yeah, there are lots of them. And so if you mix it with those, then yeah, certainly we'll have oxidation of ethanol, complete oxidation. And there are lots of them, including things like permanganate, dichromate, etc. So that was this. So the equations, I think that's where a lot of people lost a lot of points, were the equations there. But that's just practice, you know. That's why I did, how many lab periods do we do for metathesis and redox? A lot, you know, for practice. All right, so I'm gonna move on though. So chapter 7, we'll just do it sometime next week. Just an additional little bonus to recoup some lost points from this. How, what?
How many points you're gonna make it for?
Yeah, well, I'm going to make it, actually the way, this is why I waited on it. It's not going to sound like a lot of points, but I'm going to make it like 6 and, I think it was 6.5 points or 6.25 points. Because the highest score was like a 93.75 or something. So then I'll just normalize it to 100. And so maybe that person will get 100, but I don't want to go over 100, you know? And then we'll do it that way. So like six, and then I'll just make it like not one question, but multiple questions, multiple little questions, because, you know, I think a lot of people can just do one step, like this thing. You probably, you know, if you got a strong base like soda polish, you probably could do it. You know, it's just how you write it. If I wrote this differently, I was thinking, I'll write this differently, like if I wrote it like sodium, or just write it sulfide and water. I think most people would get it, sulfide and water. You know, it's just like having to do these extra little steps here that trip people up. But that's the case, because what I found for advanced, most of the advanced problems are just like this, an extra step or two before something you've done before, you know, something that's not too bad. A lot of them are like that. Anyway, we're going to go back to quantum. So, you know, metal, we're talking about black body. Metals are pretty good black bodies. What's happening in here is you have a metal here. Let's just take some iron, or actually, let's take some tungsten. Do you know the symbol for tungsten? W. We'll just take some solid tungsten. And in this tungsten, there are electrons. And these electrons are pretty mobile. You know, electrons in metals have very low resistance. They're what we call kind of loosely held. You know, loosely held, we have a word for that. That's called a delocalized. And something that's tightly held is localized, like it's localized on an atom. So we have delocalized electrons in metals. And these delocalized electrons can move around in the metals. And so these are mobile, delocalized electrons. And that's just, you know, there are different models for the bonding. The very simplest model is called the electron C model for bonding. You heard of that one? Where the electrons form an ocean, you know, and the electrons, like water in the ocean, can move around. And so there are different ways you can excite these electrons. You know, if it didn't meet any resistance in going from point A to point B here, then it would be called a superconductor. But you know, the atoms are vibrating, and the atoms vibrating is going to cause some resistance as electrons try to move. But we're going to, we don't have to worry about that for right now. We're just going to ignore it. And there are different ways we can excite the electrons. One way we can excite the electrons is by getting them to move, you know, by putting a power source here. And in other words, getting them to move by electricity. Electricity is the flow of electrons. Or we could heat it up, you know, just put it in the flame, like I did the stainless steel there. But what happens is the electrons get excited. As electrons get excited, you know, when we think about electrons, how are they going to get excited? They're just going to move. You know, it's kinetic energy, so they'll start to move. And so these electrons start to move. And then what we're going to do is we're going to look at something called an energy level diagram. And the energy level diagram just is some arbitrary energy scale. It could be E or U or H. You know, all those are just energy. E and U are the same. H is different. You know what's different about H? H is just slightly different.
Is it heat?
H is not heat. Heat is transfer of kinetic energy from a hot body to a cold body. And so this water is at room temperature. Everything else is at room temperature. Is that heat? Is room temperature the same thing as heat? Yeah, it could be cold. I mean, it could be cold in here if we have hotter objects, or it could be warm in here if we have colder objects around. And this is the transfer. And so the internal energy here is the total energy, but H is also the internal energy, but it's internal energy with the PV state included. You know, H is U plus PV, and we look at PV state to figure out how the system interacts. This is for the system. How the system interacts with the surroundings, you know. Anyway, this is also not easy because most people don't understand the difference between H and U. And then they go on to take a thermodynamics class, and then they struggle, like everybody in my class did, because nobody pays attention to this stuff. So eventually it clicks, but for right now, we're just going to think. So we have an electron here. The electron is what we call in the ground state. The ground state's like the bottom here. And then what we could do is we could excite it to higher energy states. It depends on how high we want to go. You know, for example, we could go a little bit. And so we excite the electron a little bit, or we could excite it a lot. And what we end up with is we can excite it, you know, we excite it up here, and then it doesn't stay up here forever. Let's say it drops back down here. It might emit infrared, let's say. Or we excite a little bit higher in energy. We excite a little bit higher in energy, it might drop down to emit red light, because energy is conserved. And so if it absorbs enough energy to get up here, then as it drops down, it could release a red photon. You You know, that's one way it could lose energy. There are other ways it could lose energy as well. But we can excite it a little bit more, and then it should release what color? Yeah, like orange, etc. And so we just keep exciting it to higher and higher energies, and pretty soon it's going to glow what color? White hot, yeah. Once we excite it. And then eventually it goes to UV. But there's the UV, remember the UV catastrophe? We don't have to worry about that. We are not going to spend any time. And I'm not going to test you on the UV catastrophe. But the UV catastrophe was used to fit it to an equation, and that equation forced the energy to be quantized. Even though the energy is quantized, what we see here is a continuum of energies allowed. And so we call this a continuum. We have an analogy here with gravitational potential energy. I'm going to steal this from the Chem 4 book. Because if I have a ramp like this, can I go any height up the ramp I want? Is there any forbidden heights up the ramp? So this is the height. And so I could have a continuum of heights from the ground state up to whatever excited state I want. And so this is a continuum. So one of the confusing things is if I have a continuum of energies, then, in the UV catastrophe, how is energy quantized?
I have a question on the diagram. So what's this energy level diagram telling us?
It just tells us how high up in potential energy we are. Okay, just like this. This person can go up this high, right? That's higher in energy. If they fall off from here, they're gonna lose that energy. And they can lose the energy in different ways. They could maybe slide back down, walk back down, or jump off. Over here, we're just gonna jump off. If we climb up to here, rather than cascading down, we could cascade down and release little bits of energy, in a sequence. Or we could just jump off. If we jump off here, we're gonna emit orange light. If somebody jumps off here, they might emit a scream and then a thud, something like that. But in this case, there's a continuum of energies allowed because the person can go up to any height they want. Any potential energy is allowed. In other words, all gravitational potential energies are allowed here. When we're talking about black bodies, Planck, in order to describe black body radiation mathematically, what was observed in experiment, had to say that not all energies are allowed, but if not all energies are allowed, then why do we see a full rainbow of colors? Were there any colors missing in the rainbow when you went outside and looked? No. This is kind of like the sun. In the sun has what's called a plasma. And the sun is a black body too. It's a black body emitter. And so in the sun, we have electrons, and we can excite those electrons. Electrons can be excited. Excited just means they go to a higher energy state versus to wherever they start off with. They don't have to start off with a ground state. We could start off here and then go up. In the sun, there are excited electrons already in the sun. And these excited electrons don't stay excited forever. They're going to drop back down and then emit light. Mm-hmm.
So is the light emitted until they're at a certain energy level and then they go back to a ground level?
The light that's emitted, is going to do something, and so it'll be absorbed by something like maybe our eyes, you know, the light's emitted, it's absorbed by something like a detector or something else. But the energy, that energy is still going to be conserved. And so when the photon of light hits your eyes, it does something, you know, to the rods or whatever.
I'm just like wondering what it means to like jump off. Like if the analogy has to do with gravitational energy, what does it have to do with like the electron? Like what are the excited electrons doing? Are they still
The excited electrons, when this drops back down to here, then it loses energy. Where does that energy go? That energy goes into emission of a photon. That's where the energy ends up. And so the electron's going to drop down, and then after the electron drops down, the photon is emitted. It depends on how big that drop is. So what Planck was saying is that what Planck was saying is like this is the ball analogy I use. The red light that's emitted here are little balls, you know, and orange lights are bigger balls. But you can't have any, like, for example, you can't have the 1.5 photons or 1.5 balls. It's either going to be 0 balls, 1 ball, 2 balls, 3 balls. And so the odd thing is that you can't have any energy of red light you want. You know, for example, I want a little bit of red light, I want a lot of red light in terms of energy. No, it's going to come in little packets. These packets are called photons. And so that means that and the packets are very small, so it seems like it's a continuum. And so that's where it's quantized. It's not quantized here. We're going to get the full rainbow of colors. But when we look at each color, like an infrared photon is going to be smaller. So let's say, and it depends on the wavelength. So if I have an infrared photon, it's going to be quite small, but I can have 1 infrared photon, 2 infrared photons, 3 infrared, but I can't have anything in between. And so in that sense, it's quantized. So it's quantized by what size the photon is, you know, in terms of energy. But it's a continuum in the sense that I can have any energy I want. So that's an analogy. So the hydrogen atom was expected to be a black body. And so metals act as a black body. The sun acts as a black body. The H atom should act as a black body. Because the H atom, this has a proton and electron. So if I have a proton and electron, then I should be able to excite the electron to any energy I want. So this is like if you have a car and you're driving the car, can you go any speed you want, you know, up to within a certain limit? You know, let's say nobody's blocking you. Yeah. I mean, can you go 0 miles an hour? Can you go 1 mile an hour? Can you go 2 miles an hour? Can you go 1.5 miles an hour? Yeah. Can you go 1.4999 miles an hour? Yeah. This is over here when we're talking about quantization, we can have 1 photon, 2 photons, 3 photons, but we cannot have 1.5 photons. But over here we could have any size photon we want. Just once we pick a size, then it's quantized. Now, the reason I'm bringing this up is there's 2 ways of thinking about quantization in quantum mechanics. One way is like this with Planck's. You know, we have a continuum of balls or photons, but each photon is quantized. The other way of thinking about quantization, or this thing about energies here, is this. When we look at the energy level diagram for hydrogen, and so we'll just put some generic energy unit here. It turns out if the electrons, let's say down here, then not all energies are allowed. And so for the hydrogen atom, I could go up to this energy here. If the hydrogen atom electron gets excited to this energy and then it falls back down to the ground state, we'll call this the ground state here. And this is going to be called an excited state here. Then what happens is I release a photon, and that photon is red at 656 nanometers. But let's say I wanted red light at 650 nanometers or red light at 750 nanometers. Did you see any red light at 750 nanometers? You didn't. There was none. And so what that told people was that you cannot excite the electron with any energy. So this is like driving a car. You can't, all of a sudden you can't drive 1 mile. You can't drive 2 miles. The only speed you can drive is 0 and then 15 miles an hour. But you can't drive anything in between. And so this was the second, they didn't call this a catastrophe, but it was like a catastrophe. This was the second catastrophe of classical physics. This is when people started to question, is classical physics, does it even work? Because why would an electron not be able to move any speed it wants? It's just an electron circling a proton. And so if you have an electron circling a proton, can it go slow and a little bit faster, a little bit faster? No, it can't. It can go this speed and then it has to jump to the next speed. So you can go, let's say 15 miles an hour, 30 miles an hour is the next speed that's allowed. And that means anything between 15 miles an hour and 30 miles an hour is forbidden. And so we call these forbidden energies here. There's other allowed ones in here, but this is forbidden. Forbidden. And so what about the electron? You know, the physics about it. The electron's just a particle, right? This is moving. Why can't the particle move at any speed? You know, I can excite it a little bit or I can excite it a lot, you know, by doing different things to it. So that wasn't, I mean, that was a mystery. Not only that, okay, so that's the first allowed in the visible. This is the visible. This is why I didn't write this completely. And then we have another allowed energy, and this next allowed, it would be like this would be like the first floor of the building, and this would be like the second floor. But although we're going to call this the first floor here. So this is the first floor of this. This would be like the second floor. We could go up to the third floor. If we go up to the third floor here and then drop down, it's going to emit a green. And the green, it doesn't emit any green. It emits a green at, you don't have to memorize these numbers. It emits a green at XXX nanometers. Not any green. And then the next allowed one is the fourth up here. So this is 2, 3. We go to the fourth, then it emits the blue. And then finally, if we go up to the fifth, it emits the violet. So if we drop down from the fifth floor to the first floor, we get a violet photon. And these are very specific. Specifically defined. Later on, people saw that there's a sixth, and seventh, and then there's things in between here, you know, where we get the infrared and the ultraviolet up here. But the main question is why can't the electron move at any speed at once? Do you have the answer? Well, that's the observation, but what is the answer to that? And so that would be next. You know, what would cause this to not have a continuous spectrum? So if we try to make a light bulb out of a hydrogen atom, it doesn't work. The light we get is not white light. The light we get is a line spectrum where we see red, and then green, and then blue, and then violet. So we get a line spectrum rather than a rainbow of colors. And then what that means is that these are all forbidden energies. So is there something about the structure of this that is preventing the electron? I mean, what else is there? You know, what else is there is just an electron in empty space, so why should it behave like this? That's the second catastrophe. Do you know what the third catastrophe was? They don't call it a catastrophe again. But the third catastrophe is this. What happens when a negative and a positive are close to one another? Do they repel or do they attract? They attract. So why doesn't the electron and the proton come together? What's keeping them apart? Is there like a miniature wall in here that we don't see? Because electron and proton should come.
The nuclear force.
The nuclear force holds the protons together in the nucleus.
Yeah.
But the nuclear force does not push the electron away. It's not the nuclear force. So, first catastrophe was trying to describe the UV emission of a black body. The second catastrophe kind of is, why do we have forbidden energies for the electron? And this third catastrophe is, why doesn't the electron, they say, spiral into the nucleus? Like a satellite that lost its orbit, spiral into Earth. And so everybody wants to know why, and they want a theory. A theory would be a fundamental explanation of what's happening, or a fundamental description of what's happening. But for us, nothing. And so what we come up with is, have you heard of a postulate? A postulate is something that you just take without proof. And so the postulate is this. Why are there forbidden energies? Well, that's the way it is. They're forbidden energies. Is that a very satisfying description of what's happening? No. But you just got to take it because that's the way nature behaves. This is for Bohr. Bohr postulated that they're forbidden energies because there are forbidden energies. It's like a circular argument. They're forbidden energies because they're forbidden energies. And these forbidden energies, electrons can't go there. Why doesn't the electron spiral into the nucleus? Because the electron does not spiral into the nucleus. Is that very good? No. And so he just postulated this. Bohr postulated that the electrons occupy orbits. There are allowed orbits and forbidden orbits. the electron cannot spiral into the nucleus because the lowest energy allowed orbit is what we call the first orbit. And since it can't go below the first orbit, it can't get into the nucleus. And so this would be the first orbit. And so the electron can occupy this. And then, do you know the next orbit it can occupy? The next orbit is the second orbit. And then the next orbit over here this would be the third orbit. And then out here we have the fourth orbit. Anything in between the orbits is forbidden. So this whole area is forbidden, forbidden. Forbidden. And so that's all the electron can go. So Bohr modified classical physics. Classical physics is Newtonian physics, Newton's laws, and came up with these equations. The radius of the orbit, r, depends on which orbit we're looking at, n. So n is the first, the second, the third. So n is equal to 1, 2, 3, etc. All the way up to, you know what the furthest orbit away is? Infinity. And so out here, way out here, we'll have an orbit that's an infinite. And so there are infinite number of orbits. If there are an infinite number of orbits, why are there forbidden orbits? Well, it's weird. If there are an infinite number of orbits, you'd think all of the orbits would be covered, but they aren't. There's an infinite number of forbidden orbits. In fact, there are more forbidden orbits than there are allowed orbits. How does that work? Well, we don't have to think about that. We can figure out the radius of the orbit. The radius of the orbit is equal to what we say R0. The first orbit is, I shouldn't say R0, say R1. Although it is called 0. It's called A0 or R0. But I'm going to just put the number in here. It's equal to 0.53 angstroms over n squared. And so the first orbit is, n is equal to 1. So the first orbit comes out at 0.53 angstroms. The second orbit is going to come at 0.53. Actually, since we're into picometers, if I use picometers, how many picometers is that? I timed out as 53 picometers. This one will be 53, let's switch to picometers so I don't have to use a decimal point. 53 picometers divided by 4. So this will be 1/4. Oops, that's not right, because it would be getting smaller. Sorry, this is not right, this equation here. The equation is equal to n squared times the reference orbit, which is R0, which is 53 picometers. This is even easier. And so the first orbit would be 53 picometers. The second orbit is going to be n squared times 53, which would be 4 times. So that would be about 200 picometers. This would be the second orbit. The third orbit would be what? How many times our first orbit? It would be 3 squared times 53 picometers, which would be 9 times. 9 times 50 is about how many picometers? About 450 picometers out? Is that about right? So we're at about 50, and then we go out to about 200, and now we're about what? 400? 450, 470? Yeah, okay. And the fourth orbit's gonna be 4 squared. It's gonna be 16 times out there. So the fourth orbit is way out here. I'm not gonna draw it because we're running out of board space, right? But what would the infinite orbit be? R infinity is equal to infinity squared times R0, or R1 actually, I should call it 53 picometers. And so this is gonna be infinitely far apart. And so we call this the electron. If the electron occupies this orbital, it's been ionized.
So is that a constant? 53 picometers?
Yes, it's a constant. It's called A0 or R0, but I'm not going to use 0 because zero is kind of, 0 is for the reference, but 0 is not actually one of these. We could have the first. There's no n equals 0. 0 squared would be 0. So an electron in this orbit would be ionized, would be completely separated from the proton. An electron in this orbit is completely separated from the proton. We call it ionized. And so how much energy does it take to ionize? Do we need ionizing radiation to ionize the hydrogen atom? Maybe, maybe not. Let's see what kind of energy is required to ionize it. So we go back over here, and then also from this Bohr, this is called Bohr theory. You know, he came up with the hypothesis. The hypothesis was that the electrons occupy these orbits, and then that led to Bohr theory. And so we have E sub n. E sub n is equal to R sub, let's see, R sub h over n squared. I'll have to talk about R sub h is a constant. It's called the Rydberg constant, or the Rydberg constant. And it's like 2.178 times 10 to the minus 19 joules. It's a very small number, but we'll look at that. And so here, at the first orbit, we have E1. E1, the energy of the electron here is, this is just minus R sub h over 1 squared. And so it's just minus R sub h. E2 is equal to minus R sub h over 4. E3 is equal to minus R sub h over 9. E infinity is equal to what? Is equal to minus R sub h over infinity squared, which is going to approach what? 0. And so this generates a different kind of energy level diagram because we're going to change the 0 point. Before, when we're thinking about potential energy, at what point is the potential energy 0? You know, well, it depends. If I'm looking at gravitational potential energy, do you know where the absolute gravitational potential energy would be 0 at? The center of the Earth. If I'm standing on the floor here I'm not at absolute zero. I'd have to go deeper. But usually I'm not gonna go all the way to the center of the Earth. We'll just call sea level or the floor here 0. Oops, I forgot to move my camera this way. Here. And so what we can have is we can have an arbitrary 0. And so this is the 0 that was set. The 0 that was set was like this. When the energy here is at 0, then the electron's been ionized. If you bring the electron closer and closer to the nucleus, now I have to draw an infinite number of lines. If I draw an infinite number of lines, are there any gaps? Yes, there are actually gaps. But at the top here, the gaps are so small, it looks like a continuum. And then as I get closer and closer down here, the gaps grow bigger. And then this would be the lowest energy. The lowest energy I can have is minus R sub h. That's like minus 2.179. Or actually it's 2.179 because I got the minus R there. I'll just do R sub h, minus 2.179 comes down to minus 19 joules. And then up here we have 0 joules worth of energy. So we go down in energy as the electron gets closer. This is n equal 1, 2, 3, 4, ... all the way to n equals infinity. And so the weird thing is this, the radius diverges out to infinity. The energy converges to 0. So as the radius is going out to infinity, the energy is converging to 0. And so it's kind of weird in a way. So the Bohr model had success in predicting. We could predict things like the ionization energy. The ionization energy is taking an electron from the ground floor and then bringing it up to the top floor here. And so we'll have to look at delta E for that. How much energy does it take? We're going to call this delta E of ionization. So delta E of ionization is just equal to E final minus E initial. E final is this one, minus R sub h over N final squared. E initial is minus R sub h over N initial squared. And then what I'm going to do is I'm going to factor out minus R sub h. So this is going to be minus R sub h 1 over N final squared minus 1 over N initial squared. And this is called the Rydberg equation here, delta E. I'm sorry? Rydberg equation. It's called the Rydberg equation. R-H-Y-D-B-E-R-G. R sub h is called the Rydberg constant. All right, so I'm going to calculate my delta E of ionization. My delta E of ionization is just going to be minus R sub h over 1 over N final squared, that would be infinity squared, minus 1 over N initial squared, that would be 1 squared. So this is going to give me 1 over infinity squared is going to give me 0. 0 minus 1 is just minus 1. So it's just going to be minus R sub h. And minus times a minus is going to give me a plus. Actually, yeah, minus times a minus will give me a plus. So I'm looking at plus 2.179 times 10 to the minus 19 joules. Hopefully I remembered that correctly. But I'll be able to find out. Does that seem like very much energy to you? That's barely any energy. Like I asked you before, how much coffee can you heat up with that many joules worth of energy?
No problem.
Nothing. I mean, it would be nothing. It's nothing because we live in the macroscopic world, but if you live in the particulate world, is that a lot of energy? Yes, that's a lot of energy. That's a lot of energy, but what we need to do is, our frame of reference is the macroscopic frame. What do I need to do in order to bring it more to the levels of energy that we deal with? I'm gonna ionize it with, I don't know, ionizing radiation. Let's see. So I have an electron. The electron is in this first orbit, and so what I'm going to do is I'm going to hit this with a photon. And so I want to know what kind of photon I'm going to need to get this to move out to the infinity. And so I'm going to knock this out with a photon here, such that this electron goes away to infinity. It doesn't literally have to go to infinity, it just has to get far enough that the proton has no interaction with it. Yeah, so what is it? So this is why we have to think in terms of energies. When we think in terms of energies, we're thinking in terms of energy for an individual particle versus energy of a blank particles. We talked about this last time. When we're dealing with these calculations, we always got to think, are we dealing with per particle or per atom, per electron, or are we dealing with per blank? Mole, right. And so when I look at this energy is per mole of hydrogen atoms or per hydrogen atom? Per hydrogen atom. That's a lot of energy per hydrogen atom. This is per H atom. That's one single atom. All right, so what we need is a photon of this energy here to do that. And when we use the equation, this Einstein equation here, E the photon, this is just for one photon only. So what a lot of people do is they accidentally use the wrong energies. They use the per mole energy here, and they get some ridiculous number. But E of the photon is equal to h nu, which is equal to hc over lambda. So what I'm going to do is I'm going to solve this for lambda. Lambda is equal to hc over E of the photon. H is 6.626 times 10 to the minus 34 joules times seconds. C is 2.998 times 10 to the 8 meters per second, divided by E, the photon, which is going to be 2.179 times 10 to the minus 19 joules. Can somebody calculate that? I haven't used the Rydberg constant in a while, so it's too fuzzy. You look it up. I'd look it up on my phone, but. Oops. Let me change this. My memory isn't that good. It's 2.178 times 10 to the minus 18. I would have seen that when we do the calculation because I know what wavelength of light this is. But redo the calculation with this. Does somebody have the wavelength? 3.95 times 10 to the minus 11? Positive 11? Oh. Wow, something's off. Something else is off.
I got a different number.
You got a different, what did you get?
9.12 to the times 10 to the negative 18.
9.12 times 10 to the negative 18?
Oh wait, hold on, the exponent might be wrong. Hold on.
I got 9.12 times 10 to the negative 8.
Times 10 to the negative 8?
Yeah.
Still off a little bit.
Yeah, that's what I got too.
That's what you got too? 2.178 times 10 to the minus 18 joules. They say. Yeah, this one's closer. So that would be this is meters. So in terms of 10 to the minus 9, which way do I move the decimal? So if I make the exponential term smaller, 10 to the minus 9 is smaller than 10 to the minus 8, then I make the coefficient bigger, or do I make the coefficient smaller? Bigger. So I get 91.2 times 10 to the minus 9 meters. 10 to the minus 9 is nano, so this is 91.2 nanometers. Do you know where that light is?
In like the gamma rays.
I'm sorry?
Maybe like on the higher end, maybe like gamma rays.
Yeah, where do you think 91.2 nanometers is in the electromagnetic spectrum? Is that X-ray, gamma ray? No, we don't need X-rays or gamma rays to ionize hydrogen. All we need is ultraviolet. This is ultraviolet. Ultraviolet spans over orders of magnitude in terms of wavelength, and it starts at 390 and goes down from there. So 250 is ultraviolet, 100's ultraviolet. It just goes, yeah, spans several orders of magnitude. So this is going to be ultraviolet. So we just need ultraviolet light to ionize hydrogen. So if I have a UV photon here of 91.2 nanometers, that's enough to kick it all the way up here. So basically any energy greater, than this should do it. The situation here is this. If I have an energy greater than this, then it just knocks it off with more speed, This is just enough to make it up here, but more energy, it'll knock it off. This is what we saw in the photoelectric effect. But that photoelectric effect, you do those calculations in physics. I'm not going to worry about that in Chem. It's just conservation of energy. The other situation is here. Let's say I have some other light. So this will be h nu. H nu is just the common abbreviation for a photon of light, h nu. I could try to excite it here, but if I have too weak of a photon, it doesn't make it up to the next floor. So the other analogy for quantization of energy is stair steps. This is also from Chem 4. And so if we look at gravitational potential energy, which depends on the height, you know, can you be at any height you want? No. You know, we have the first floor here, we have the second, we have the third, the fourth, the fifth. So you can be on the first or the second step, but you can't be in between. And so these are forbidden heights here. So anything in between these is forbidden. The lowest is the first, and then the second is the next energy, the third, and the fourth. So this generates an energy level diagram like this, where if we don't have enough energy to lift our foot up to the second floor, we're not gonna make it, right? We're just gonna stay on the first floor. You might have enough energy to jump up to the fourth floor. If you have enough energy to jump up to the fourth floor, then you're good. But what if you only have enough energy to jump up to the 3.5 floor, or 3.5 step? Are you going to make it? No, actually you're gonna end up falling all the way back down if you try to jump up to this. And so the same thing for an electron. If it doesn't have enough energy to make it up to the fourth, and it only has enough to make it up to the 3.5, no, forget it, it's gonna drop. There's gonna be no change in energy. And so that's the forbidden and the allowed. But do you see stairs in an atom? Or do you see floors of a building in an atom? You know, are there little miniature floors or miniature stairs? No. And so it still doesn't quite answer the question, you know, why is energy quantized in an atom? And so this was taken without proof. It was taken without proof because it was very successful. Because what did it predict? You know what it predicted? Theories have to predict something. And what this theory predicted is that there are other lines that we don't see. And these other lines that we don't see, so for example, we see these ones here. The third to the second is the red. And then the fourth to the second is the blue. And then the fifth to the second is green. And the sixth to the second is violet. We see other lines too. So for example, if we go from the second to the first, it's invisible because it's in the ultraviolet. So this is UV. If you go to the third to the second, this is UV2. Fourth to the, not fourth to the second, third to the first. Fourth to the first is also UV. So what we see are this. In our visible spectrum, we have our red, blue, green, violet. And so this is the visible. But there are invisible lines here. The invisible lines would be the UV. And there are invisible lines in the infrared. So for example, let's say if we go from the fourth to the third, that's IR. And the fifth to the third, this is also in the IR, or that might be in the UV. And so there are IR lines here too. This will be in the UV. So it was successful. It was successful at predicting this. We could calculate the wavelength of the red line. And so one of the successes is pick any of these lines, we can calculate it. Each of these lines corresponds to a transition. So over here, this is the n equals, what we call the n equals 3 to the n equals 2 transition. That's going to give us our red line. So if I wanted to do this, then I'll just use the Rydberg equation. Delta E is equal to minus R to the H 1 over n final squared minus 1 over n initial squared. And then we could calculate this. This is going to be delta E for n equals 3 going to n equals 2. And so n equals 2 is our final. And so that would be 1 over 2 squared minus n equals 3 is our initial. So that would be 3 squared. So we're starting off higher and dropping down to lower energy is going to emit light. And so we're going to have negative energy, which would be emission of energy, which is emission of light. And so what we'll have is minus r sub h, 1/4 minus 1/9. And so we just punch that in our calculator using the invert key. So you do 4 invert minus 9 invert equals, and then multiply that by r sub h. And that gives us the energy, and then we can calculate the wavelength. And so we calculate this, and then we calculate the lambda, and the lambda equals our 656 nanometers. So in that sense, it's quite successful. We could pick any of these lines here and calculate the wavelength. But there's something, there's something kind of nagging, and that's something that's kind of nagging is why? Why does the electron have these forbidden energies? It doesn't quite make sense still. The Bohr model was also successful, so it was success. The success was it was able to predict all these lines. That's great. And then they're able to apply Bohr model to other one-electron species by modifying the energy equation. And so we can come up with En, and this is going to equal Z squared. Z is the number of protons. This is the atomic number. R sub h, n squared r sub h. One electron species. What are other, do you know any other one electron species? Oh, I know the H atom. It's one electron species. Can you think of any other one electron species? What else has one electron? The helium ion, the lithium 2+ ion, the beryllium 3+ ion. Are these very common?
Do they even have?
These are rare. You'd have to make them. They're so unstable. Rare and unstable. But this is another success story. So Bohr had some successes, but he had one catastrophic failure. So this would be the Bohr catastrophe. The Bohr catastrophe is that it doesn't apply to anything else. It fails for everything else. Fails for everything else, which is everything. So if the theory can't predict the helium atom, then there's something wrong. Fails for everything else, such as helium. Helium's the second most simplest atom after hydrogen. So this is history. So Bohr theory, theories can evolve, and that's what happened with the Bohr theory. Bohr theory was partially abandoned. Partially because the idea of quantized energy, the idea of forbidden energies and allowed energies was retained. But there are two developments that led to modern quantum mechanics. Quantum mechanics is the theory that replaced the Bohr. And so, two developments led to modern quantum mechanics replacing Bohr theory. Bohr theory, we talk in terms of orbits. Orbits turns out to be wrong. And sometimes people get this confused because they sound similar. Quantum mechanics doesn't deal with orbits anymore. In quantum theory, orbits are completely abandoned. The whole idea of orbits, not everything in terms of the math, but the whole idea turns out there. Instead, we look at something called orbitals. So, orbits and orbitals are totally different. But what were the two developments? The two developments, one was the de Broglie wave-particle duality. Two is the Heisenberg uncertainty principle. So let's talk about de Broglie. Now, when we look at wave-particle duality, we already see it with light. So an example is light. Light kind of behaves both. We know it's wave properties, but it also has particle properties, and that's the photon. The photon of light is like a particle of light, h nu. And so we have wave and particle-like properties. And so light behaves kind of like a particle. And that is, if I'm shining light, I can't have any amount. It's like, can you have any amount of sugar you want in your coffee? And you think, yeah, I can. I could put 2 teaspoons, 3 teaspoons, or whatever I want in my coffee, right? Can you have a half a teaspoon in it? Yeah, you can, but what happens if you're on a diet and you say, well, I don't want a teaspoon, I want just a single sugar molecule in my coffee. Is that possible? Yeah, you could put a single sugar molecule in your coffee. It'd be very difficult, but you can do it. But let's say, I've been good this week. I'm gonna put 1.5 sugar molecules in my coffee. Maybe not 2 molecules, just 1.5 sugar molecules. Is that possible? It's impossible because sugar is quantized. I can have 1 molecule, 2 molecules, 3 molecules, but I can't have anything in between, correct? But you don't notice it because it's only when it gets extremely at that extreme level, right? We don't notice it. Actually, that's the same reason for quantum mechanics. You don't really notice it until, and this is why Newton's laws were so successful. Newton's laws were so successful because most of the things we look at were quite large, but when you go down to very, very small level, then it's not. And so this is what happens with matter. Matter also has weight and wave and particle behavior. You know, 1/2 mv squared, where v is the velocity. So you have a baseball. Baseball's going, let's say, 60 miles per hour. Could the baseball go any speed it wants, or are there forbidden speeds for the baseball? Oddly enough, there are kind of, it's kind of weird to think about, but there are forbidden, I don't know, speeds or energies or something. And so it's kind of weird to think about, but the way we think about it is like this. And probably the easiest way of thinking about it is, as this ball is moving at 60 miles per hour, it's like a particle. But there's a wavelength associated with it, and this is called matter wave. This is not the same. So this is lambda is not equal to c over nu. Okay, this is for light only. Over here we have it, you know. Lambda is equal to c over nu, and E is equal to h nu, which is equal to hc over lambda. We have those. But for matter waves, we have something called the de Broglie equation for this. And so if I wanted the wavelength of the baseball, you don't have to memorize the de Broglie equation because we don't really use it much. Actually, they're different. This equation is going to be different than our book, but it's different because of how we handle h. H is the Planck's constant, the same Planck's constant in light. So in that sense, it's the same, but when you look at the equation, it's a bit different. Normally we look at we could look at the energies as well, but this is going to be equal to h. M is the mass, and v is the velocity. The h is extremely small, 10 to the minus 34. And so what happens is this wavelength is extremely small wavelength. That's why the wavelength is so small, that's why we didn't really notice it. Okay, so to get the significance of this, then what we need to do is we need to look at something called standing waves and something called particle in a box. Particle in a box isn't really talked about that much in our book. I'm just going to use a particle in a box analogy. So standing waves are like an instrument string. If I have a string instrument, can the string have any energy it wants? Like, for example, can you have like a one-string guitar or a one-string violin or something like that and just play any energy, any tone that you want? No, we can't. The energy is going to depend on how long that string is, right? And also other characteristics of the string. And it turns out we can't, because if you pluck the string, then you have to plug it hard enough that it starts to vibrate. And the first allowed vibration is what we call a half wavelength. And so this is 1/2 lambda. And so it could vibrate up and down like this. So pluck it, and it's vibrating. The next allowed energy is where we have a full wavelength. We call this 2 times 1/2 lambda. This is 1 times 1/2 lambda. What's the next allowed energy? The next allowed energy is when we can fit 3 half wavelengths in here like this. And so this would be 3 times 1/2 lambda. But we can't have anything in between because then it wouldn't connect. The string's got to be connected here and here. And so if we try to put a quarter wavelength in there, will it work? The quarter wavelength won't work because it would have to vibrate like this. And so 1/4 lambda is forbidden. You see that there? And so string instruments are quantized. There are allowed energies and forbidden energies. Here. Now we're going to go to a particle in a box. The particle in a box, I'm going to talk about a whale in an aquarium. So I'll just use this whale in an aquarium analogy. A whale is like this string instrument here. You know, the string is kind of confined. So let's say we have a whale here. And let's say the aquarium's quite small. So we're going to do this in number of kicks of the tail. Let's say 1 kick of the tail and it's already at the other end. And then maybe you could get 2 kicks of the tail in there. So when a whale is confined to a small space, you know, it needs to do a complete kick of the tail, then maybe 1 kick here, 2 kicks here, it's going to be moving faster. 3 kicks, it's going to be moving even faster across the aquarium. But let's say it's one of these things where you can't get a half a kick. Maybe you could get a half a kick in there, but it's got to be a full kick or 2 kicks, you know. And so in this sense, the whale in an aquarium is quantized. Versus a whale in the ocean. If the whale's in the open ocean, can it go any speed it wants? Yeah, it can go any speed it wants. So a whale in the ocean is like this. So here we have to worry about the wavelength or the frequency of the kicks. When a whale is quantized in an aquarium, it could get 1 kick. It could get 2 kicks of the tail. It could get 3 kicks of the tail. But it's going to be quantized. Over here, the wavelength of the kicks is so small, it's negligible. And so the whale in the open ocean can have pretty much any speed it wants. And so this is like the baseball. In the baseball here, let's say I have 1 trillion half wavelengths in there. What's the next allowed energy? So if I have 1 trillion lambdas, the next allowed one is 1 trillion and 1. Okay. What's the next one allowed after that? The next one allowed after that is 1 trillion and 2. Do you think there's going to be much difference between 1 trillion kicks and 1 trillion and 2 kicks within that distance? It's negligible. And so essentially this baseball has a continuum of allowed ones because this baseball is like the whale in the open ocean. it could get 1 billion kicks here or 1 billion and 1 kicks. There's very little difference in energy, but there's going to be a tiny increment in speed. It's going to go just a hair faster, right? Versus here, if it tries to get 1 kick versus 2 kicks is going to be a big jump in speed compared to 1 kick, right? And so a whale in an aquarium is like an electron in an atom. The aquarium is the atom, the electron is the whale. And so when a whale is in an aquarium, then the kicks are important. Well, so the same thing with an electron. If you have an electron in an atom, then it depends on how many kicks you can get. Let's say I got 3 kicks in there. What's the next allowed one? The next allowed one would be 4 kicks. Well, 4 kicks is going to be moving significantly faster, isn't it, than 3 kicks? And so there's going to be a big jump in energy here. So we don't see this quantization until we get to very small confined spaces, and then you'll notice that the wavelength makes a difference. So this is why physicists never saw this, because if you had 1 trillion kicks versus 1 trillion and 1 kicks, it's negligible. You don't notice that. And so I'll stop here.